Now let's look at the first example problem. This is a leet code problem. It's called the sum of even numbers after query. So here's the problem statement. So you are given an array of integers and then a number of queries. So here queries are really operations. So every query you will perform some update on the array and then you will compute something. So what in this problem you're asked to compute is the same. Is the sum of all the even numbers in the array. And the update you'll perform is to add a particular value to a particular index. So each update will update a single element in the array. And after the update, you will need to compute the sum of all the even numbers. So this is what the problem asks you to do. And looking at the parameters, the array has at most 10 to the 4 elements, and each array element is between negative 10 to the 4 and positive 10 to the 4. And there are 10 to the 4, up to 10 to the 4 number of queries. Given this number, there are sort of a few things you can infer. First, using int type is sufficient because the maximum number you are likely to encounter is going to be around 10 to the 8, and int can represent up to 10 to the 9. So using int is okay. We don't have to use long in Java or long in C++. And second, a quadratic algorithm is probably not going to be efficient enough. If we have an algorithm that runs in time n times q, that's probably not going to be efficient enough. And also, let's just to understand what the problem really asks, let's look at this sample input and output. So we start with an array 1, 2, 3, 4. So the sum of even number at the beginning is 6, but that's not what they are asking for. So then we look at this set of queries. The first query says it's given by 1, 0. So what that means is look at the element at index 0, add 1 to that number. So then after this query, the array becomes 2, 2, 3, 4, and 2 is just recently updated. So when the array is 2, 2, 3, 4, there are 3 even numbers, 2, 2, and 4, so the sum is 8. So that's why the first element in the output array is 8. And then the second query is negative 3, 1. So this says subtract 3 from the element at index 1. So then the element at index 1 goes from 2 to negative 1. So at this point, we have we have 2 even numbers, 2 and 4, so they add up to 6. And the next query is add the negative 4 to the element 0, so subtract 4 from element 0, which is 2, so that becomes negative 2. So we have a 2 even number, negative 2 and 4, and the sum is 2. So and so on. So I encourage you to pause the video and think about how you solve this problem. So the natural approach is, well, if you ask me to update the array, I will do it for you, and after that I will compute the answer to the query. So this is the Java code for doing that. We go through all the queries. For each one, what the query asks to do is to add this element to add this value to the element identified by this index. So we simply do that, and then after I do the update, then I will go through all the array elements, and if it's even, I will add that to the result. So the question is this approach good, and what is the time complexity? So in general, when I have a red question on the slides, these are the things. If I'm teaching in classroom, I will ask the audience, and then I will discuss the student solution. So I encourage you to pause and think how you would answer these questions in red. So the time complexity is n times q. because this loop is executed q time, and within this loop there's another loop which is executed n times, where n is the length of the array. So then the statement in blue is executed n times q time, and this is the statement that executes the most number of times. Now the question is, can we do better? Can we improve this? In general, when we look for improvement, we look at, are we doing computation that are wasted? So oftentimes this wasted computation takes the form of redoing the same computation again and again. So think about what are the computations we're doing again and again. I think it's pretty obvious that we are summing up these even elements again and again. A lot of time they're not even changed, because every update we are only changing one element and we are summing up all the even elements. So to avoid redoing this wasted computation, what we can do is we first calculate the sum of all even number in the beginning, and then we just when we update the array, we just update that number, so we don't have to redo the computation again. So then here, let me actually turn on the pointer. Yes. So here, this line will calculate the sum of even numbers at the beginning, and then we go through all the queries. For each of the query, we will update the corresponding element, but then we also need to update the corresponding even sum. So there are different ways of writing this code, because the update, what kind of update it will occur will depend on whether the number to be updated was even before we update, and whether it become even after update. So there are different ways of writing the logic, but here I think I chose a way that's conceptually very simple. So the first thing I do is I subtract whatever contribution this case element is going to be to the even sum. So if it's even, then it's added in even sum. I'm going to subtract it because I don't know whether this number will remain even afterward. And then I update it, and after update, if the number is even, then we'll add it to the even sum. So this take care of maintaining even sum. Now, what's the complexity, time complexity of this approach? So now it becomes n plus q. We have a loop here, which loops through the array size n. And then here, this body of this loop is executed q time. But within this body, we have just a constant number of operations. So it's, every one of them, it just take a few cycles for the computer to execute. So so this is a big old Q for this loop. So by caching this even sum, we reduce the complexity from n times q to n plus q. So the lesson from this example problem is oftentimes we have a bunch of data and we want to update it, and then we want to query this data. So when that happens, we can choose different way to do it. One way is we update the underlying data and then we recompute the query answer. But these can sometimes be inefficient. And then the other way is we cache the query result, and then we figure out when we do the update, how would that affect the query result. So in fact, this trade-off between what intermediate result to store and will be very common when you both writing program for say data structure or just solving real world problem. Oftentimes you need to make this decision: what kind of data do you cache? And actually the right decision will also depend on the ratio of update versus query. So sometimes you may have a lots of update, and only after many updates, then you will get a query to answer. In that case, caching the query result may not be the best approach. So in this problem, every update is followed by a query. So then we do want to cache the query result. But for other cases, this in a sense, data structure is about figuring out what to cache so that you can do computation efficiently.